Nisarg is someone who I was first introduced through Vector Institute, actually in committee work. So some of, you get older and you start doing more committees and more responsibilities, and you're always like, oh, all these committees. But one of the good things about committee work, especially the ones that evaluate applications, this one being the faculty affiliates committee, is that you get introduced to great people because you see people's profiles coming across your desk. And I saw what Nisarg was up to, and then I think we had an opportunity to meet face to face at there's a Jeff Hinton Turing Award Symposium a year or so later, and we chatted. And when we kicked off this seminar series, I really thought we should get Nisarg out to talk about fairness and algorithms. I thought I really like this idea or this area of computer science meets economics. And one thing that really impressed me about Nisarg's work was that he had rolled it out into actual applications. So I had these websites open this morning, reminding myself, but he's got this Split It site, which you should check out. Go to his website and find what he's been doing. But it's a website where people can split complicated things, I guess. Say someone passes away in the family and you need to organize their belongings, but also things just like rent, which often comes up in the lives of graduate students, how to allocate when the rooms are not all the same, all uniform, and some rooms are nicer than other rooms. I remember that as a student. And then RoboVote, for sort of AI enhanced voting and decision making. So these are things that we are dealing with on our everyday lives. So the math is sometimes complicated, and the science is it takes a lot of time to get to the point where Nisarg is right now. But these are problems that we're dealing with day to day. So that's what I really like about this research, and that's why I'm delighted to introduce Nisarg.
Thanks, Graham, for that wonderful introduction. So Okay, so thanks again for inviting me. It's actually a pleasure to be here and be talking to such a diverse group of people. So because I was expecting the group to be diverse, I've made my slides kind of less technical and more oriented towards the high level takeaway messages. That said, I would still kind of get into the details of what the exact fairness notions I talk about. All right, and I'll talk about, in the beginning of the talk, I'll talk about my work on this fair division theory, which is this area at the intersection of computer science and microeconomics. And I'll talk about how these fairness notions emerged from this literature. And then towards the end of the talk, I'll describe how these kind of fairness notions can be applied to machine learning applications. Okay, so as you all know, algorithms are now making decisions pretty ubiquitously in the real world. From deciding who gets loans or bails to deciding which ads to serve, whom to hire, or even sometimes in more high-stakes scenarios such as how to drive cars autonomously or whose organ should be given to whom. And because of this, there has been a recent surge in interest in making sure that these algorithms are making these decisions fairly. And the surge is partly fueled by popular accounts where it was made clear that the algorithms were in fact making decisions in an unfair manner. And while this surge in interest in fairness is a pretty recent phenomenon in the machine learning literature or the algorithmic fairness literature, fairness has been studied in the context of resource allocation for almost a century in this field called social choice theory, which sits within microeconomics. So here is a paper from 1948 by Hugo Steinhaus in Econometrica called The Problem of Fair Division. And this paper arguably started this field of fair division. And it talks about a setting that has now become famous as the cake cutting setting, which some of you may have heard about. And then later, this kind of study of fairness was extended to other settings of fair division, such as allocating indivisible goods, which I'll talk more about in a few moments. And in the last few decades, computer scientists also got interested in this area, which gave rise to the field of computational social choice, which studies algorithms for making these kind of collective decisions based on the individual preferences. And what's nice about this computational social choice literature is that it doesn't only focus on fairness in algorithmic decision making. Fairness is but one aspect that it considers, other aspects being the efficiency of the decision, how do you actually elicit the preferences of the participants who are affected by the decisions, what kind of incentives this process generates for these participants. Maybe they can misrepresent their preferences in order to benefit from the system. And also a question that is a bit less explored than the question of fairness, which is ethics and how that is different from fairness. In today's talk, I'll mainly be focusing on three facets of collective decision making: fairness, efficiency, and incentives. And as Graham mentioned, my collaborators and I developed this not-for-profit website called splitit.org back in 2014. And this website basically takes its motto is to take classic solutions from the computational social choice literature and these solutions that are provably fair and make them available to people for their daily use in a free manner. Okay, so Splitit offers currently 5 different applications. There is the share rent applications, which, as Graham mentioned, is pretty popular with students. If 5 students, let's say, rent an apartment, then and there is a total rent, then what this application does is it asks each person to place a value on each of the rooms. And then using this input, it finds a way to assign the different rooms to different students and place a rent on each room that sums up to the total rent of the apartment, such that each person would prefer to have the room that is assigned to them at the rent that it is charged, then take somebody else's room at the rent that they are charged. Okay, so nobody would have any envy towards another person. Everybody would be happy, the most happy with the room that they are assigned at the rent that it is assigned. Okay, so this is a notion that's called envy freeness, which is going to play a big role in the talk that I'll give today. And this is kind of a very non-trivial result in computational social choice or in social choice theory in general, that an envy-free rent division even exists. And it's something that surprises a lot of people when they approach this problem without looking at Splitit first, and then they come to Splitit and try it. Another application is Split Fare, where a group of friends who take a cab together but drop off at different locations, it allows them to split the total fare in a fair manner between them. Assign credit is an application where you can, if you work in a group and you want to divide credit, basically how much each person contributed to this group effort, then what it does is it asks each participant to identify, in their opinion, the relative contributions of the other group members. And then by combining these inputs from all the group members, it finds a fair assignment of credit. And this is actually something that's quite popular with teachers because they love kind of having their students work in groups on some projects. And then the students go to this website, they each individually say what they think was the relative contribution of the other group members, and then the teacher can assign grade based on the credit that is assigned to each group member, rather than just giving credit equally to all the group members. Dividing goods applications is a simple application where you just have a bunch of items that you want to divide between different people, and these people want the items. So this, I won't say much about this because the first half of the talk is focused exactly on this application. And finally, distribute tasks is kind of a flipped version of divide goods, where the items that are being divided are not goods, but rather chores or bads that people don't want. And so the algorithms kind of fundamentally change when you go from dividing goods to dividing bads. Okay, so the dividing goods is a simple kind of process of taking m items and dividing them between n people. But this has a lot of real world applications. So here are some of the applications that, based on the user feedback, people have actually used Splitit for. So this includes inheritance division, divorce settlement, a group of friends who bought a season ticket for some basketball matches together, and then they wanted to divide the tickets to the individual games between them. Online gamers who work as a group and find some loot somewhere, and now they want to divide the loot between the individual players. Or a group of art collectors who bought some artwork over a period of 10 years by pooling in their money, and now they want to divide the artwork. So what happened is that back in one important characteristic of this divide goods application is that the goods are often indivisible, which is that you can't take a good and you can't split it between different people. And when you have these indivisible goods, you can't really get envy freeness, because imagine that you have just one item and you have two people who both want the item. You have to give the item to one of the two people, and whoever you give it to, the other person would envy them. Okay, so because envy freeness is not achievable in this setting where you can't charge people money, when we deployed Split back in 2014, Split used an algorithm that tried to satisfy some relaxations of this NV freeness guarantee. And it turned out that these relaxations were pretty weak, which weren't really guaranteeing a good amount of fairness in the outcomes that they were generating. And this led to a bunch of user complaints where people complained about the unfairness of the outcomes that they saw. So here is an example email. This was from a group of 4 brothers who wanted to divide an inheritance of some 30 plus furniture items. So one of the brothers just went onto the website and he tried the website out on a bunch of demo instances. And on some of these instances, the outcome wasn't really matching his expectations. So what he did is he went ahead and created a so-called minimum working example for us. And to save you the effort to read this email, here is his minimum working example. He says, let's imagine that there are 3 people and there are 5 identical candies that we want to divide between these 3 people. So what can you do? Well, the only fair thing to do is to give 2 of the people 2 candies each, and then the third person would get a single candy. It's a bit unfair to the third person, but what else can you do if you don't have 6 candies? Now, surprisingly to him and to us, Split actually gave 3 candies to the same person back in 2014 when it was launched, and the remaining 2 people were only left with a single candy each. So this was quite surprising, and we dove into what the algorithm did on this particular instance, and the fairness relaxation that it was trying to achieve basically said on this instance that, look, I can't really guarantee that each person gets at least 2 candies because I don't have 6 candies to divide. So let me at least guarantee that each person gets at least a single candy. And then subject to that fairness constraint, let me maximize the total happiness of all the participants. Now, the problem with maximizing total happiness is that because all the participants like the candies equally, it doesn't really matter where those remaining 2 candies go for the purpose of maximizing total happiness. So Split just broke ties by giving both those remaining candies to the same person. And this was obviously unfair. So this led us to try and find better fairness definitions that we can aim to achieve and designing algorithms that achieve those fairness notions. So before I dive into the details, let me just describe the setting a bit more formally first. So the input to our problem is just this value matrix, where as columns, you have the different items that you want to divide. And as rows, you have the different participants or agents who are participating in this process. And each agent assigns a value to each item. And the values are additive. They are assumed to be additive in this particular problem. So for example, if the guy at the top, if he receives both the painting and the car, then his value for that bundle would be 67 plus 150. Okay, so a bit more formally, let's say capital N is a set of N agents, capital M is a set of M indivisible goods, and then each agent's preferences are represented by this valuation function VI, which assigns a non-negative value to every possible bundle of goods that the agent might be allocated. Okay? And as I said, these valuations are additive. So the value that an agent has for a bundle of goods is simply the sum of her values for the individual goods in the bundle. And our goal is to find an allocation A, which is simply a partition of the set of items between the N people, where AI is the bundle that is given to agent I, and for which the agent has utility VI of AI. So we want to find an allocation that is fair. And as I said before, in this literature, the classic gold standard notion of fairness that you would want to achieve if possible is NV freeness, which just says that no agent should desire the allocation given to another agent more than the allocation that is given to themselves. Okay, so if you take any pair of agents I and J, then the value that agent I places on her own bundle AI should be at least as much as the value that agent I places on the bundle given to agent J, AJ. So note that on both sides of the equation, we have the same valuation function of agent I. We are just evaluating everything from the perspective of agent I. And obviously the definition is symmetric. So you also don't want agent J to be envying agent I. Okay, this holds for all pairs of agents. But of course, as I said, this notion is not exactly achievable because we have these indivisible goods. And therefore, the old mechanism that was deployed on Split was relying on a hierarchy of weak relaxations. But after the feedback from this user, we actually found a pretty strong relaxation of NV freeness that at least would have solved the problem on that particular instance. And this relaxation is called NV freeness up to 1 good. And this says that, look, I cannot really prevent agents from envying other agents. That's just not possible when I have indivisible goods. So at least I should make sure that if agent I envies agent J, then that envy is in some sense limited. If I just take some good from agent J's bundle, and if I just hide it for a moment, then agent I wouldn't envy the remaining bundle that agent J is given. So formally, for all pairs of agents I and J, there should be some good in J's bundle, such that if you remove that good for a moment, then agent I doesn't envy the remaining bundle given to agent J compared to her own allocation. Note the quantifier here, the sum good. Okay, so in particular, at least if you hide the good from agent J's bundle that agent I values the most, then agent I shouldn't envy the remaining bundle. Now, in some sense, it's a pretty minimal relaxation of envy freeness because it limits the envy that agents have for other agents to only one good in their bundle. Okay, and you can't really get down from 1 to 0. It turns out that actually, if you want this fairness notion, which by the way would solve the issue as I mentioned on the previous instance, because it would in fact guarantee that 2 of the participants are given 2 candies each and a third participant is given 1 candy, because if you give 3 candies to the same person and another person has only 1 candy, then they would envy the person with 3 candies by more than 1 good. Now, if you just want to achieve envy freeness up to 1 good, it turns out you are in luck because you can achieve it using a very simple allocation procedure called round robin. So what you do is you just have all the items lined up in an arbitrary order. You have the agents lined up in a cyclic order. Okay, so if you have the blue, orange, and green agents, then you line them up as follows: blue, orange, green, blue, orange, green, blue, orange, green, dot, dot, dot. Now, what you do is that agents take turns according to this cyclic order. And in their turn, an agent basically just looks at all the items that are still available on the table. And among these items, she picks the item that she likes the most according to her own valuation function. Okay, so the blue agent goes first, picks an item that she likes the most. Then the orange agent looks at the remaining items, picks one that she likes the most, and so on and so forth. Now, my claim is that this simple procedure guarantees that the allocation that is computed is envy-free up to 1 good. Let me briefly explain why. So let's see why the green agent wouldn't envy the blue or the orange agents up to 1 good in their allocations. Okay, so what I'm going to do is I'm going to divide this allocation into different phases, where the first phase is going to start when the green agent picks the first item. The second phase starts when the green agent picks the second item, and so on. So in each phase, each agent gets to pick one item, exactly one item, and the green agent is the first to act in each phase. Okay, so if you look at just the 3 items that are allocated in phase 1, the green agent definitely likes the item that she picked at least as much as the items that other people picked after her in that phase, because she could have picked those items if she wanted. Similarly, in phase 2, the green agent likes the item that she picked at least as much as the items that anybody else picked. Okay. So if you just combine all the allocations across the different phases and forget about these 2 allocations given before the first phase started, then just in those phases, the green agent wouldn't envy the other agents at all. So the only reason that the green agent would envy the blue or the orange agent is for this one item that they each got to pick before the green agent even started picking items. So if you just hide this first item that the blue agent picked, the green agent wouldn't envy the blue agent for the remaining items that the blue agent has. Similarly, if you just ignore that one item that the orange agent picked first, then the green agent wouldn't envy the orange agent for the remaining items that the orange agent has. So this is awesome because it's a definition that's very simple to explain, and it's a procedure that's very intuitive, something that many people already use in real world. But the problem is that these allocations that are generated by round robin are not efficient. So here I'm referring to a very basic notion of economic efficiency, which is called Pareto Optimality. And the definition, the formal definition seems complex, but let me just parse it in simple words. So Pareto Optimality just says that if you compute an allocation A, then there shouldn't be another allocation B, which gives each agent at least as much happiness as before, and some agent strictly more happiness than before. Because if you can actually find a way to redivide the items among the agents such that nobody is worse off and somebody is strictly better off, then clearly that redivision is a better way to allocate items. It doesn't harm anyone and it makes some people better off. So what Pareto optimality says is that you want to find an allocation A such that there is no Pareto improvement. There is no way to redivide the items to make somebody better off without harming anyone else. Okay? That would mean that your allocation is truly, at least in some minimal sense, it's efficient. The problem with round robin is that it violates Pareto optimality in a very strong sense. Once you find the allocation generated by round robin, you might actually be reallocate the items to the agents in a way that every agent likes the new set of items strictly more than they like the old set of items. Yeah, so in that sense, the allocations generated, while fair, are not very efficient. So that led us to the this question, which is, does there always exist an allocation that is both fair and efficient at the same time? So fair in the sense of envy-free up to one good, and efficient in the sense of being Pareto optimal. And the answer that we found is that indeed there always exists such an allocation, and it can be computed by maximizing the so-called Nash welfare function, which is the product of the values that people derive from their allocations. Okay, so let's see this on an example. Let's imagine that you have two individuals, a brother and a sister, who are trying to divide an estate consisting of three items: a house, a painting, and a car. So the brother has some values for the three items. Okay, so that's his valuations. The sister also places some value on the three items. So that's her valuation. And now you just want to find an allocation of the items to the agents that maximizes the product of values. So let's look at this particular allocation where the brother gets the house and the sister gets the painting and the car. So the brother's value for the house is 5, and the sister's value for the painting and the car combined is 4 plus 5, which is 9. So you add values across the items that a single person is given, but then you multiply the values across the people. So 5 times 9 is 45. And I'm claiming that on this particular instance, this 45 is the highest product that you can get. So this is the allocation that would be returned by this maximum Nash welfare algorithm. So without going into details about why use this algorithm, let me just tell you the result, which is that if you maximize Nash welfare, then the allocation that is returned will always be both envy-free up to one good and Pareto optimal. All right, so that we developed this algorithm back in 2015, and we deployed this on Splitit, and then after that we haven't received any complaints about unfairness of the algorithm. So while we haven't really done any formal user studies, this tells me that the algorithm is kind of working well. One thing that I want to point out before moving on to other problems is that the literature on fair division is full of as many open questions as it's full of impressive results. So for example, from this paper, we had 2 open questions which are still open and which are worked on very much in the community. So one open question is that can you compute an allocation that is EF1 and PO in polynomial time? Okay, so it's a computational question. Now, maximizing the product of values, as you can imagine, is a pretty difficult objective function to optimize. And in fact, it is strongly NP hard and it is APX hard. So, if you don't want to maximize the Nash welfare, but you just want to compute some allocation that is EF1 plus PO, we don't know if that can be done in polynomial time. What was later shown by a 2018 paper is that you can at least do it in pseudo polynomial time. Note that you cannot even maximize the Nash welfare in pseudo polynomial time because it is strongly NP hard. But on Splitit, we have deployed a Nash welfare implementation based on integer linear programming that works reasonably well for even instances like 200 items and 50 agents, and most real world instances aren't larger than that. Although we recently had an instance where an estate of up to 1,000 items was divided, but the number of agents were pretty small. It was something like 10, so it still worked reasonably well for that. Another open question that popped up from this work was related to a fairness notion that we defined, which was kind of between EF1 and envy freeness. Okay, so it's stronger than envy freeness up to one good, but still weaker than envy freeness. And this we refer to as envy freeness up to any good. So recall that for NV freeness up to 1 good, you don't want agent I to envy agent J after removing some good from agent J's bundle. There should be some good in J's bundle such that hiding this good makes the envy vanish. EFX makes that notion stronger by saying that if you hide any good from J's bundle, any good whatsoever, there should be enough to eliminate the envy that I has for J. Okay, so the envy that I has for J should be limited to even the least valuable good that I has in J's bundle. So the only difference between EF1 and EFX is the quantifier here. Any good from J's bundle, removing that should be enough to eliminate the envy. And here it's even an open question to determine if there always exists an EFX allocation. Forget about Pareto Optimality. If you just want to get EFX, can you always achieve it? Or is there an instance where none of the allocations are EFX? Okay, so this itself is an open question. And there was some very nice progress made just this year. So this year at EC 2020, the student best paper, its main result was that EFX always exists for 3 agents. Okay, but for 4 or more agents, this is still open. All right. So we started with this notions of fairness that are based on NV freeness. We looked at this NV freeness up to 1 good. We saw that you can achieve that along with Pareto optimality. And then at one point, we started asking this question, is this kind of fairness enough? Okay, note that NV freeness and its relaxations are more individual levels of fairness notions. They look at an individual looking towards another individual and determining whether they envy this other individual or not. But it doesn't talk anything about groups of agents, which is something that's popular in recent work on fairness. So the answer to my earlier question is that no, individual fairness is not enough. And here is an example that kind of illustrates this nicely. So imagine that you have 4 agents. You have a circle agent who only likes circle goods. Okay, so she has value 1 for all the circle goods and 0 for all the square goods. Imagine that you have a square agent who only likes square goods. Okay, so again, she has value 1 for all the square goods, 0 for all the circle goods. And then the remaining 2 agents are flexible. They like any good. And imagine that we have 2 circle goods and 2 square goods that we divide as follows. We give each flexible agent 1 circle and 1 square good, and we give nothing to the circle or square agents. Now, first thing to notice is that this allocation, while it's seemingly unfair, it is actually envy-free up to 1 good. Note that the circle agent does envy the flexible agents, but if you remove 1 good, that the circle good from the flexible agent's allocation, then the circle good doesn't really envy the flexible agent anymore because he doesn't really like the square good at all. Okay, for him, receiving the square good is same as receiving nothing at all. Similarly, the square agent envies the flexible agent, but if you remove the square good, then she doesn't envy the flexible agent anymore. But my claim is that even though this is fair at the individual level up to 1 good, it's not fair at the group level even up to 1 good. Okay, so to do that, let's consider 2 groups of agents. A group S that consists of the circle and the square agent, and group T that consists of the 2 flexible agents. My claim is that if group S were to be given group T's resources, and they were allowed to redistribute those resources amongst themselves, then here is how they would do it. The circle agent would take both the circle goods, and the square agent would take both the square goods. So not only is this better for them than what they had before, but it's better by more than 1 good each. Okay. Note that the circle agent is better off by 2 goods compared to his previous allocation, which was nothing. And similarly, the square agent is also better off by 2 goods than his previous allocation, which was nothing. Okay. So in this sense, even though an allocation can be individually fair up to 1 good, it might violate fairness at the group level, even up to 1 good. So to make this notion more concrete, before I get into the formalization, just want to mention that group level fairness can also come up in many real world applications where resources are being divided. For example, if you are a school district trying to divide educational resources between teachers, then you not only want to be fair to the individual teachers, you may want to be fair to teachers who belong to different schools, different geographic area, different grades, different subjects, or different race or gender. So there are all these different groups of agents that you might want to be fair to. And what's important is that these groups can sometimes be overlapping. As I said, you can define a group of teachers based on race. You can also define a group of teachers based on the grade that they teach. And these groups can be very, very much overlapping. So one thing that we wanted to define is how do you formalize a notion of fairness that considers all these different overlapping groups, which is very different to some of the fairness notions that are studied in machine learning, where the groups are disjoint and well defined. Another important thing is that in some applications, the groups may not be given to you pre-specified. Okay, you might want to achieve some kind of fairness to all possible groups of agents at the same time without knowing the groups in advance. And so along that line of thought, last year we had a paper in AAAI where we proposed a notion of group fairness that actually is stronger than individual fairness. So this group fairness actually implies NV freeness, which obviously implies some other notions as well. And I won't go into the detail of what this notion is mathematically because it's a bit complex, but I just want to explain the intuition behind this notion. So this group fairness notion says that no group of agents S should envy another group of agents T. Okay? Now, the first thing to notice here is that it applies to all groups S and T. So there are 2 raised to n possible choices of S, 2 raised to n possible choices of T, and none of the groups S should envy any other group T. Now, what does it mean to envy? The envy is defined in a similar sense as what we did in the previous example, which is that we let group S take the resources given to group T and then redivide it amongst themselves. And then we see if group S is better off compared to their previous allocation by using group T's resources. Okay, so basically, the notion of better off is same as this Pareto improvement, which is we ask whether each member in group S is at least as well off as before, and some member can be strictly better off if they take group T's resources rather than the resources that they are given themselves. But there is one caveat here, which is that there is no mention of the sizes of these groups. Certainly, if a group consisting of 2 agents looks at a group consisting of 1,000 agents, those 1,000 agents may be allocated many more resources than these 2 agents are allocated. So certainly, if they take all the resources given to these 1,000 agents and redivide it amongst themselves, they would be much better off. So what we do is after they redivide it amongst themselves, we scale their utility by a factor, which is the size of S divided by size of T. Okay, so if we are looking at a group of 2 agents envying a group of 1,000 agents, we let them take all the resources given to the 1,000 agents. But after they redivide these resources amongst themselves, we divide their final utility by a factor of 500. And then we ask if this new utility is a Pareto improvement over what they had previously. And then you can, since group fairness is a stronger notion than NV freeness, which by the way, NV freeness is something you can get by only restricting the S and T to be of singleton size. Okay, so when S and T are singleton, it basically just means that no individual agent I should envy another individual agent J. But clearly, since NV freeness is not achievable with indivisible goods, you can't achieve group fairness as well. So you have to rely on some kind of relaxations of up to 1 good. And I won't go into the detailed definition of group fairness up to 1 good, but I just want to point out the result, which is that if you just maximize Nash welfare, not only is this individually fair up to 1 good, it's also actually group fair up to 1 good. Okay? And in fact, if you want to just achieve group fairness up to 1 good, and if you are willing to sacrifice Pareto efficiency, then you don't even need to globally maximize this Nash welfare function. A so-called local optimum of this Nash welfare function is sufficient. And the local optimum basically just means that you shouldn't be able to make a local move where you just take 1 good from 1 agent, give it to another agent, and that improves the Nash welfare. And the benefit of this local optimum is that it can be computed in pseudo polynomial time. And here there is another open question, which is whether you can compute this in polynomial time. Okay, so that's also an open question. All right, so at a high level, we started from this individual notion of fairness like EF1. And then we said that EF1 is not enough. We need actually fairness at the group level. So we defined this group fairness and then GF1. And then we found out that actually Nash welfare already satisfies group fairness up to 1 good. So you don't even need to change the algorithm that we have deployed so far. And then we started asking the question, is this fair enough now? Or do we need some more kind of stronger notion of fairness? And the answer was that this wasn't actually fair enough. And to see why, let's look at another simple example. This time we have the same 3 agents, but we have 4 identical candies. And all the notions that we have looked at so far, they basically say the same thing on this instance, that you want to give 2 candies to one of the 3 people, and the remaining 2 people would get a single candy each. Again, it's slightly unfair, but this is the most fair that you can be according to the notions that we have seen so far. The question is, who should get 2 candies? Now, if you do this on SplitIt, if you go ahead on SplitIt and create a dummy instance, it turns out that SplitIt always breaks size in favor of the first agent who is listed in the ordering. Okay, so if you list the 3 agents as Alice, Bob, and Claire, Alice would always get 2 candies, no matter how many times you run this instance. Okay, so that seems like some kind of preferential treatment for one agent over other agents. Now, of course, if the goods were divisible, then this problem just wouldn't arise, because then you could give 1 candy to each of the 3 people and then split the 4th candy in equal parts between the 3 people. And as you may have guessed, you can kind of mimic this allocation by using randomization. Okay, so if I'm allowed to randomize between allocations, then what I can do is I can find a randomization where each agent in expectation gets 1.33 candies. But I have to be careful if I use a bad randomization. So for example, here is one thing I can do. I can take a 3-sided die, roll it, choose an agent at random, and give them all the 4 candies. Now in expectation, each agent is receiving the same number of candies. So there is fairness in expectation. But after the dice is rolled, so after if you look at the exposed world, in the exposed world, there is no fairness. Okay, so even though there is ex ante fairness here, there is no exposed fairness. But of course, this is a purposefully chosen terrible randomization. What you really want to do is you want to give each person at least 1 candy, and only for the 4th candy, you want to randomly pick an agent and give them the 4th candy. And this randomization would not only be ex ante fair in expectation, but also exposed fair after the coins are tossed and regardless of what the coin outcomes are. So that is the question that we addressed in this work published this year, which is, can we get both ex ante fairness and exposed fairness at the same time? Okay. Now, in this simple instance, it was very simple. It basically just came down to a tie breaking, which we did randomly because all the goods were identical. But when you have goods that are not identical, and if people can place different values on the different items, then this question is no longer very trivial. Okay. So for example, as a notion of exposed fairness, you can look at the notion of envy freeness up to 1 good that we already saw is achievable. And as the notion of ex ante fairness, you can look at exact envy freeness in expected values. Okay. So the question then becomes, can I randomize over allocations that are envy free up to 1 good? And by doing that, can I make sure that in expectation, no agent envies any other agent at all? Okay. So in expectation, there is no envy. And even after you toss the coins, envy is pretty much limited. Can you achieve both of these things at the same time? And that question is highly non-trivial compared to this silly example. So that is the question that we addressed in this paper, except we didn't just look at envy freeness as the notion of ex ante guarantee. We looked at a bunch of other guarantees. And similarly, we also looked at a bunch of different exposed guarantees. And then we asked which combinations of ex ante and exposed guarantees can you achieve at the same time? And the main result from the paper was that for the EF and EF1 combination, you can actually achieve it. So there always exists a distribution over EF1 allocations that achieves exact envy freeness in expectation. And in fact, one such distribution can be computed in polynomial time. Okay. Then for some of the other combinations, we gave some possibility and impossibility results. And again, there are as many open questions as questions solved. So for example, one very interesting and very kind of important open question is, instead of randomizing over EF1 allocations which are just fair, what if I want to randomize over allocations that are both fair and efficient? Okay, so they satisfy both EF1 and Pareto optimality. So these are the kind of allocations that maximizing Nash welfare gives you. Can you randomize over this smaller set of allocations to still achieve envy freeness exactly in expectation? And that's an important question that is still open from this work. All right. Now, before I move on to machine learning, let me just say a few words about incentives, because that's one aspect that I haven't really touched here so far. In fact, all the algorithms that I described so far, they sometimes give incentives to agents to misreport their valuations. And to prevent these kind of incentives, the game theory literature offers a very strong desideratum called strategy proofness. Strategy proofness says that no agent should be able to benefit by misreporting their preferences, regardless of what other agents are doing. Okay? So if you fix the reports of the other agents and make them arbitrary, regardless of these reports, if agent I's true valuation function is VI, And by reporting this true valuation function VI, if agent I receives some bundle of goods AI, and if by reporting a false valuation VI prime, if the agent receives some different bundle of goods AI prime, then the value that agent has for the bundle received under honest reporting should be at least as much as the value that she has for the bundle received under dishonest reporting. So, and this value is according to the true valuation function. So regardless of what anyone else is doing, I just have no incentive to manipulate because I cannot ever get a better value by manipulating. So of course, this is a very strong notion to achieve. This kind of notion is achievable when you have the flexibility of charging agents payments. So for example, in auctions, many of you may be familiar with the idea of second price auctions, which is actually a strategy proof auction. And the reason you can achieve strategy proofness is you can charge agents payments. But in classical fair division, you cannot charge agent payments. And even in the absence of this ability, it is very difficult to achieve strategy proofness. In fact, for this fair division problem, Klaus and Miyagawa showed in 2001 that if you have two agents and additive valuations, the only way you can get strategy proofness along with Pareto optimality, this basic notion of efficiency, is to run some sort of a serial dictatorship. And I won't get into the details here, but the important thing here is that this construction, this kind of negative result, requires each agent having at least 3 different possible values for the different goods. So that raises the question, what if you restrict yourself to a setting where agents only have binary values? Okay, so where each agent either likes a good and has value 1 for it, or dislikes a good and has value 0 for it. So what we were able to show this year is that if you are in this binary world, then actually maximizing Nash welfare is just pretty much awesome across the board. If you do it deterministically, then along with a specific tie breaking, it is not only group fair up to 1 good and Pareto optimal, as I said before, but it's also strategy proof and it can be computed in polynomial time. And if you are allowed to randomize, then by randomizing over these allocations that maximize Nash welfare, you can actually get ex ante group fairness without losing any of the other ex post properties. So basically, without going too much into detail, maximizing Nash welfare gives you all the possible properties that you might want in the binary world. And in fact, the resistance to manipulations doesn't only happen at the individual level, it also extends to group level. So formally, maximizing Nash welfare actually satisfies what's called group strategy proofness, where even groups of agents cannot simultaneously manipulate such that each person in the group is better off than before. Okay, so that's enough about this literature on fair division. I wanted to give you some context as to where these definitions come from. I now want to describe how in my recent work, I've taken these fairness notions from the computational social choice literature and applied them to machine learning tasks such as classification, clustering, and reinforcement learning. By the way, Graham, if there are any questions, I am not really monitoring the chat or the participants panel. So if there are any hands raised or any questions on the chat, feel free to just stop me and I can answer those midway as well.
Okay, sure. I have been taking a look and I haven't seen anything. There was a comment, okay, but I will stop you if anything that comes up. And it's good for people to know that they can raise their hands, especially if they have clarifying questions along the way.
Yeah, exactly. Yeah, because for clarification questions, it's too late at the end of the talk. So
great.
All right. So there are a few different machine learning settings that I want to look at, but the one where fairness has arguably been explored the most is the classification setting. So let's look at the standard fair classification model, where you have a set of agents who are being classified, and each agent or each individual is represented by a vector of non-sensitive attributes. Let's call it X. Then there is also a sensitive attribute associated with this individual, which basically usually represents the membership of this individual to a certain class, either it's race or gender or something else. And for simplicity, let's just imagine that this attribute A is binary. It's either 0 or 1. And in some settings, there is a binary ground truth as well. So for example, if you are using a machine learning classification algorithm to decide who should get a loan and who shouldn't get a loan, then there is a binary ground truth which represents whether this individual is actually going to be able to repay the loan or not. And then you have a binary classification outcome, which is to either give the loan to this person or not give the loan to this person, which is supposed to match the binary ground truth in principle. Now, for this standard model, a host of different fairness notions have been proposed over the last 5 or 6 years. And I expect that many of you would already be familiar with some of these notions, so I won't go too much into detail for these notions. But there is a demographic parity, which basically requires that the rate of positive treatment, which is classification outcome 1, which you can think of it as giving the loan or giving bail, something that people want to get. So the rate of this positive treatment should be equal between the two or more groups. The equalized odds definition basically conditions not only on the group membership but also on the ground truth, and then requires that the rate of positive treatment should be equal between the two groups that are defined based on both race, both the sensitive attribute and the ground truth. One thing that I want to mention about these notions is that they generalize pretty well to situations where the groups are non-binary. So for example, if you have more than 2 races or more than 2 types of gender, then these notions generalize very easily and seamlessly. But they don't generalize well when your classification outcomes can be non-binary. So let's take a look at this silly example where, let's say, you are deciding loan applications, but instead of just deciding whether each person should get a loan or not get a loan, when you give them a loan, there are 5 different types of loan that you can give them. And these people have basically different preferences over which of those 6 outcomes they want. Okay, basically receiving any of the 5 different types of loans or not receiving the loan at all. Now, it is very difficult to extend notions like demographic parity and equalized odds, which are really defined for binary outcomes, to this kind of non-binary setting. You can club all the 5 outcomes which are giving different types of loans into one outcome and call it a positive treatment. But then, while you would ensure that the rate of positive treatment is the same between different groups, it could be possible that one group really gets the kind of loans that they want, while another group gets loans, but not exactly the kind of loans that they want. Okay? In that sense, the treatment to these two groups can really be unfair. Now, preference-based fairness notions like envy-freeness extend very naturally to this kind of setting because they are already defined as a function of the preferences that the agents have. But the problem is that they are too strong in machine learning settings. Okay? If I have only a limited number of loans of each type to give, I can't really require that no agent would envy any other individual, because some agent is going to get a loan and some agent is not going to get a loan. And the person who doesn't get a loan would envy the person who gets a loan. So the idea that we explored with some students was to look at this kind of envy-freeness notion, but on average across groups of agents. So we weaken this envy-freeness and we apply it only on average across groups. So kind of more formally, if you have a pair of groups of agents, S1 and S2, then instead of asking that no individual I envies another individual J, what you do is you look at a random individual I from group S1 and a random individual J from group S2, and then you ask that on average, agent I doesn't envy agent J. So in expectation, there is no envy between these two groups. So this is one-sided definition where you are asking basically that group S1 should not envy group S2. You can also apply the same definition in reverse and ask that group S2 also shouldn't envy group S1. There are also other notions that we generalize in this work. For example, there is a notion of equitability, which requires that the value that agent I derives from her own allocation is equal to the value that agent J derives from her allocation. So it compares the value of two different agents rather than looking at everything only from the perspective of agent I. And you can also apply this basically in the same fashion at a group level. And what we show is that these notions are nice in the sense that they seamlessly extend the previous notions to this multi-class classification setting. So for example, if you want to recover something like demographic parity, all you need to do is define these groups by the sensitive attributes. If you want to recover equalized odds, then all you need to do is define the groups both by the sensitive attributes and by the ground truth. So if you just define the groups correctly, then in the binary setting, you can recover notions like demographic parity and equalized odds. So in that sense, these notions generalize the standard notions seamlessly to the setting where you have more than 2 outcomes. Another thing that we show is that these notions have good generalization errors, just like demographic parity or equalized odds. So even if you want to impose this kind of fairness notions across exponentially many pairs of groups at the same time, all you need is polynomially many training samples in order to ensure that if you achieve low amounts of fairness violation on the training set, then you'll also have low amounts of fairness violation on the test set. But I won't go into the technical details of this theorem, so I encourage you to check out the paper if you are interested. There are also some other benefits. For example, one nice thing is that these notions are kind of applicable to both settings with a ground truth and without a ground truth. All you have to do is define your groups of agents across which you want to ensure fairness appropriately, given whether there is depending on whether there is a ground truth or not. We also do some simulations and some experiments with real data and show that this kind of fairness has relatively low impact on the loss function that a principal may have in mind. But again, for details, I encourage you to check out the paper. All right, now I want to move on to another problem, which is clustering. So the standard clustering problem is that you are given a set of n data points and you want to place k cluster centers among these n data points. Now, for a fairness perspective, just like the classification world, the fairness perspective comes in when these data points actually represent agents who are being treated. And one application where clustering is used is to locate some kind of public facilities. So each cluster center represents the location where a public facility is going to be built. And then each agent would access the nearest public facility and wants this nearest public facility to be as close to their location as possible. So formally, your input is locations of n different agents and the locations potentially of some possible cluster centers if you cannot place the cluster center anywhere in the space. You are also given a distance metric d that measures all the distances, and your goal is to output a set of k cluster centers, and then you can define the cost to each agent or each data point I as the distance to the nearest cluster center among the k cluster centers that you have picked. And then the question is again, how do I make sure that my clustering, the locations where I build the public facilities, it's treating even groups of agents fairly? So here, there is a notion that is very much applicable, which is called the core. So I haven't mentioned the core fairness up until now, but it's actually something that is implied by group fairness. So remember, I earlier talked about this group fairness where I didn't want any group to envy any other group. The core is actually something that's implied by group fairness. But if you look at the core notion just specifically for this clustering problem, then it boils down to something very intuitive. This notion says that, look, I'm placing k public facilities between n agents. So any group of at least n over k agents deserve one public facility to serve them. They are entitled to one public facility. So if this group of agents S, let's call it S, that has at least n over k agents, if they are able to find a location Y, which is closer to each member in the group than the nearest public facility that they have, then this is some kind of a violation of group fairness. Okay, this group is entitled to have one public facility serve them, but they are able to find a location which actually serves each of them better than the current set of k locations that you have placed. So you want to try and avoid these kind of scenarios. And you can also look at approximation of this notion where you basically say that even if you take the distances of these group members to the new location that they find, and you blow these distances up by a factor of alpha, let's say alpha is something like 2 or 3, even then these distances are smaller than the current distances that they have to their nearest facilities. Okay, so the higher the alpha, the more the violation of fairness. So this notion was actually studied this year in an ICML paper. And what they showed is that exact core is actually not possible to achieve in clustering. There is an instance where none of the possible cluster centers that you can choose achieve core fairness, but you can always guarantee a 1 plus square root 2 approximation in this particular sense. And this result holds for any distance metric. So all you really need is the triangle inequality. What I showed with a student this year at an ICAL paper is that if you are in the Euclidean metric space, then you can actually improve this approximation factor to 2. We also have some computational results about the complexity of checking if a core clustering exists. And we also show some generalization error, where if you get a few sample data points, and then you find a clustering that is core or approximately core for the sample data points, then this would also be core or approximately core for the underlying distribution of points from which the samples were drawn. Finally, I want to say something about this reinforcement learning. So with some students, we also looked at this problem of multi-arm bandits. where usually you have a bunch of arms, and once you pull an arm, a principal observes some reward generated from some distribution. And the classic goal is that there is a best arm, okay, the arm that has the highest mean reward from the distribution. And if you knew all the distributions, you would just pull this best arm all the time. Okay? But since you don't know the distributions, you have to start by pulling different arms. You have to start learning the distributions from which their rewards are being sampled. And you want to ultimately converge to pulling the best arm all the time. And you want to measure the regret that you have compared to pulling the best arm all the time. So what we did is we looked at a multi-agent version where these arms are some kind of policy decisions. And when you pull an arm, it's not only one principle that is being affected, but n different agents are being affected. So each of the n agents observes a different reward from a different distribution when you pull an arm. So now in this multi-agent setting, there is no longer the notion of what is the best arm, because each agent might think of a different arm as different policy decision as best for them personally. But you can still define what is the fair kind of selection of arms. And we use the Nash welfare again to define a fair selection of arms. For technical reasons, we aim for the fair probabilistic selection of arms, the distribution over arms that maximizes the product of expected utilities to the different agents. And we show that you can basically learn this fair distribution over arms using with vanishing expected regret, where the regret now is measured in terms of the lost Nash welfare. All right, so that's kind of the end of the technical part of the talk. I just want to take the last maybe 5 minutes or so to go over some high-level takeaway that you should have from this talk. So one high-level takeaway is that there is a nice feedback loop between theory and practice in this kind of applications. So if you take the example of SplitIt, not only are these deployed applications based on strong theoretical foundations, results that theoretically prove that the algorithm always satisfies some kind of fairness notion or efficiency notion, but actually feedback from these deployed applications help us derive better theoretical foundations. So for example, by using the feedback from these users, from this group of 4 brothers, we were able to find this better fairness notion and a better algorithm to deploy on SplitIt. And this kind of feedback loop has worked really well. So over the past 6 years or so, SplitIt has been used by more than 200,000 people to solve a bunch of different everyday problems. The feedback of these people is not only relevant for finding problems with existing algorithms, sometimes they also point to novel real-world domains where fairness is required. So for example, back in 2015, a representative from a school district in California reached out to us with regards to the problem of fairly dividing public school facilities between charter schools, which led us to discover a different mechanism that worked well for that setting. Another takeaway is around explainability, which is something that has gotten a lot more attention recently. So one question you might have is, how do I explain these kind of fairness-based notions to the end users? So on SplitIt, we do this very easily because NV Freeness, I feel like it's very amenable to this kind of explanations. So what you can do is you can go back to each user and you can provide them an explanation as to why this decision is fair. And here is an example explanation highlighted in yellow. It tells this participant that, look, according to the value function that you reported, according to the number of points that you assigned to the different items, you were given items that were a total of 635 points out of 1,000 points. And in comparison, you assigned only 365 points to the item that this other person was assigned. Or you assigned only 500 points to the items that this other person was given. So you don't envy any of them. Similarly, sometimes you can also explain that, look, you do envy this person, but we weren't able to find an allocation that prevented envy at all. And at least if you remove this one good from this other person's bundle, then the rest of the items are assigned lower number of points according to your own valuation function than the items that you are given. And this kind of explanations, people have reported to us that they find it very helpful. Okay, some future challenges is obviously there is a need to extend this kind of study of fairness to other domains. I already mentioned allocation of public school facilities to charter schools. We have also done we have also extended this kind of notion to the problem of gerrymandering or political redistricting. Another problem called participatory budgeting, where residents of a city vote over how public budget should be allocated. There is also a need to kind of more formally analyze the price of fairness. How much do you lose in some objective function by basically ensuring fairness? Also, these fairness notions are kind of static, whereas in real world, people interact with the system over time. So there is a major open question as to how do you formalize concrete fairness notions that take the excess of time into account. And then finally, there is also an interplay between fairness and incentives. For fair division, I already mentioned that fairness is very difficult to get along with incentives unless you are in this restricted binary world. But for machine learning settings, this actually becomes a lot more interesting because there is a general perception that if you use fair algorithms, they are going to give unfair treatment to certain groups that are perceived as disadvantaged. And this has given rise to this notion that maybe the advantaged groups would want to misrepresent their sensitive attributes, at least in settings where these kind of sensitive attributes are self-reported, in order to get that advantage. So recently there were some popular news articles where a mom was arrested because she wrote down her son's gender, her son's race as black and Latino, whereas her son was actually white, because she thought that this would give him a leg up in college admissions. So we have done some preliminary studies on looking at this kind of interplay between fairness and incentives. And what we have found is that indeed fair algorithms do give some incentive to this advantaged group to misreport themselves as disadvantaged groups. Sometimes even more than the incentive that disadvantaged groups had in the first place to misreport themselves as advantaged groups under unfair algorithms. But the choice of fairness notion affects this phenomenon quite significantly. So if you choose one fairness notion over another, it does affect the level of incentives pretty significantly. Here finally is a shameless plug of the other endeavor that my collaborators and I have, which is RoboVote, where people can go and do some kind of voting decisions, either in cases where there is a ground truth answer and people just have noisy opinions over what this correct answer is, or there is no correct answer. People just, for example, want to find a good restaurant to have dinner at, and they just have different kind of preferences over which restaurant they want to go to, and they just want to arrive at some sort of consensus decision. And unlike Split-it, where we have deployed some axiomatic notions of fairness and efficiency, here we have deployed a more quantitative approach where you have some objective function in mind and you want to find the best possible approximation of this objective function subject to the information that you have available. And here are references which are available in the slides that will be made available, I suppose, or you can look at this recording afterwards, or you can also find these publications from my webpage. And that's it. Thank you.